So, my name is Alice, and thank you for coming. I'm going to be speaking a bit about Rust today, and but before I do that, I think I'm going to tell you a bit about who am I. Why should you listen to me when it comes to Rust? So, I work on the Android Rust team at Google, where I've been working on Rust drivers for the kernel, specifically with a focus on Android. In this context, I've written a driver called the binder driver, which is the first thing I did in the kernel, which recently landed upstream. Since then, I've also worked on some other drivers. Right now, I'm working on this thing called RHYL, which is a GPU driver for ARM GPUs. And then we have downstream, which is not in the upstream kernel. There's something called HMEM, which has to do with anonymous shared memory. So, and all of this is in Rust, right? So I've done a fair amount of Rust drivers by this point. Some of you may also know me from user space, where I maintain a library called Tokyo. You can think of it as the asynchronous standard library for Rust. Here's a screenshot from the official Rust website. And I'm taking this screenshot in because, so the title of this talk is, so you want to write a driver in Rust, but I think we should start a bit earlier than that. And if you remember back to Paul's talk, you had this triangle. And I think there's something similar going on here, where historically it has been very difficult to have a language which is both fast, let's say as fast as C, and it is reliable, which encompasses this memory safety thing, and this productivity thing. I mean, you can get the two others if you do some sort of proof checker thing, but that's not going to be productive at all. So, yeah, so before we get to actually how do you write a driver in Rust, I want to say a little thing about performance. And what I'm really going to say here about performance is Rust, when we're going to pick a second language for something like the kernel, one of the prerequisites is that the language you choose has to be able to at least match C. And I think that, I'm not going to go into this particular point too much, but the point is Rust, I mean, a lot of the things it does is at compile time, and so it ends up, and it uses LLVM and so on like C. So in general, it can match C, and I have seen this work out in practice as well. But I think what's more interesting is this question of reliability. And lots of you have probably already heard lots of people talking about memory safety. But one of the things I want to point out is that actually, yeah, memory safety is a big part of RHYL Rust, but it's not actually the only thing you get. Because, so one of the things that Rust is really good at is letting you define your own things you want to check in your program. So you can add your own new checks that didn't come with the language. One kind of interesting example that there was recently an article about in LWN is this idea of untrusted data, where if you get data in from user space, you want to do some sort of checking on it. And there are some patch sets to actually write an API that enforces that you do this. And there are lots of examples of this. And all that to say is that all of these features that Rust has to essentially add new checks to Rust, they can catch many logic bugs other than just your memory safety issues, which is, also has tools for. So here's one example I think is kind of interesting. So one of the things we have in Rust is that we have a lot of different pointer types. And so the idea is that, yeah, in the machine code, it's going to compile down to a pointer. And so in C, you would just use a pointer in all of those cases. But in Rust, you actually have different types depending on the ownership model. And one possible ownership model is reference counting. And Rust has something called arc, atomic reference count, which is a pointer which does that. And we actually have an implementation of arc in the kernel, our own implementation, separate from what other Rust people use. And the API is designed in such a way that if you use it from, say, Rust, you're never going to have a use after free. That's how it's designed. Now, I once explained this to someone, and I received this question. Okay, but this arc.rs file that you have in the kernel, that the kernel developers wrote, it didn't come with the language. There's unsafe Rust in there. So how can you actually guarantee anything? Well, maybe there's a bug in arc. And here, I kind of want to make an analogy. So let's say you take a bug, a driver like binder. It does a lot of reference counting in many different places. And now I say, okay, I have this new tool, and yeah, inside the tool there could be bugs, right? But it's going to remove all of your use after freeze caused by reference counting in the binder driver. Right? So there might still be bugs, but there are bugs in like the core tool and the core kernel. Like they're not really due to something you did wrong in the binder driver. Go ahead, Joel. Behind you.
Well, I would argue that that's no different from C having a ref count API in the kernel and C drivers using the ref count API. Now, obviously, you could say that, yeah, there's a bug in the implementation of the ref count API, then stuff outside of it will break. So I don't think that's the main. I think the advantage here is that ref counting is the way it's implemented. You use the borrow checker in Rust, and it breaks at compile time. That's
that's what it's about, right?
Yeah, yeah. But this slide is like saying that, okay, arc.rs has a bug and stuff outside of it breaks. That advantage, you can kind of get the same benefit from any language by making functionality common and treating it as a black box.
It has more to do with preventing the user from doing bad things with your API design. In the binder driver, there have been lots of ref counting bugs, right? Yeah. Maybe they don't call increment at the right time, or maybe they decrement 2 times when they should have decremented once. I don't know.
Yeah, we have that in the C ref count API as well. We have saturation and undercounting checks and all that.
Yeah, but those are runtime checks. If you catch this at compile time, you're going to have a better time.
Yeah, that's the big win with Rust. Yeah, the compile time breakage. Yeah.
Being able to catch things at runtime is great, but I mean, if you can catch it when you build the code, that's even better.
Thanks.
Okay, but so the point I'm really making here is that, yeah, there's unsafe code in Arc, but it doesn't matter, because one of the things that Rust is really, really good at is allowing you to encapsulate. You can take your unsafe code and put it in one component, and then the rest of your code doesn't have to be unsafe just because you used unsafe. And so here, this diagram here kind of shows what I mean. So let me just explain it. Up in the upper right, you have include. That's your usual C headers. We run them through this tool called bindjoin at build time, which generates equivalent Rust code with the same structs and the same function signatures. And so that's the binding crate. That's kind of your C headers, but in Rust. Then we have this kernel crate in the middle, part of the core kernel. And for example, for the work queue API, we have a module in here which exposes a nice-to-use idiomatic Rust interface that's safe, but internally it calls into the C work queue to do its stuff. And this means that you have your driver all the way over on the left side, and the driver is able to use this safe API to call into the work queue. And the idea is, no matter how stupid the thing is you're doing in your binder driver or whatever driver you have with the work queue, if you get it wrong, it's not going to compile. At least that's the goal of the design, right? Maybe there's a bug in the work queue, but if you do something stupid but safe in the driver, and that's use after free, well, that's a bug in the kernel crate, not in the driver. And I actually think that the results of this encapsulation are really good. So here are some real-world drivers and the amount of unsafe code that's in the driver as opposed to in this shared wrapper around the C API. The one with the most unsafe is this binder driver that I wrote for APC and Android, and part of the reason for this is that binder has this component written in C, so it's actually half C, half Rust, called binderfs, which exposes the file system, and it needs a bunch of unsafe to communicate over this boundary into the C component. That's actually also why there's unsafe in the QR code. It exposes 3 Rust functions to the C side, which the C can then call like any normal function, but then on the boundary there's a little bit of unsafe code. Okay, so this is my last slide about unsafe. So this is a quote I find kind of interesting, which is that, so let me just read it. So the world isn't black and white. No one does pure good or pure bad. It's all gray. Therefore, no one is better than anyone else, right? But, and that's kind of what I'm hearing when people say, you have unsafe code, so therefore you lose everything you have. But in reality, like, what happens in practice is that's not the case. So you can isolate the unsafe code to one place, and then you can still gain massive improvements, even if the kernel is always going to have unsafe, and it's never going to be a complete guarantee. Okay, I'm going to stop talking about unsafe code now. I want to say something about productivity, which is, and so I put this in quote, in quotation marks, but if it compiles, it works. And this is something you're going to hear from many people who are using Rust a lot. And there's a reason people say this, right? It's not that there's never bugs in Rust code, but there really is quite a lot of people who have the experience that they write some Rust code and it works on first try often. And even if your first version of the code takes a bit longer, which once you ramp up, I don't think it takes that much longer. Well, I mean, if it works on first try, that's a pretty big advantage. Of course, then there's the elephant in the room, which is how do you actually learn the language? And so I think there's 2 aspects to this. One are the people who are actually writing a Rust driver. But I'm not actually so worried about that, because if you actually have a real project that you're spending a lot of time on, and you go through the resources I'll mention later, and you ask your questions on, for example, the Rust for Linux chat room, and so on, you're going to ramp up in not that long time. It's maybe a few months. But the more worrying part is, what about the maintainer who receives a bunch of Rust code and doesn't have time to learn it? And for this case, so one aspect that I think is useful is, okay, you can, when you actually receive Rust code, and if you, review it and ask questions about it, that's actually an opportunity to learn Rust. Another thing that I've found quite helpful is either set up a video call or even do it in person if there's an appropriate conference upcoming, and then go through the patch set with the author. I've done this with multiple high-level maintainers before. Go through the patch set and talk about, like, what's this Rust code doing? And I think that works relatively well to, get you started with having an idea of what's going on. Okay, so now we're actually getting to the title of the talk. So if you're going to do anything with Rust, step 1 is you need to compile the code. And a really good place if you're doing something in the kernel is there's this quick start document, so it has a bunch of commands for a bunch of different distros for how you can install Rust. In my case, it's this one. You need the Rust compiler, standard library source code, bindgen, which is this tool I mentioned previously. And another thing that's super useful is make Rust available, which is a little tool that checks your environment and checks if you're missing anything to be able to compile Rust. And it's pretty useful for diagnosing issues with your setup. So, in general, check out the quick start guide. It has instructions for your distro, most likely, and a bunch of other useful information for compiling it. But, so, where do you go from there? So I think one nice place to look at is, well, we have a bunch of sample code. There's some of them here. There are more samples. But I want to show you a bit. I mean, I can't teach you Rust in this talk. I don't have time for that. But I want to show you a bit of one of the samples. So what I've worked on the misdevice sample myself. Well, I wrote the abstractions and Lee wrote the sample. So I'm going to show you parts of this sample and hopefully talk a little bit about how some things work in Rust, just to get you started. So in C, when you define your module, you're going to say, okay, this function is where your code starts. But in Rust, we actually do that with a type instead, a struct usually. And so here, we're saying this struct is where everything starts. And so in our case, maybe the struct is declared like this, and the fields basically become global variables, and they basically represent the module. In our case, for the misdevice, we have this thing inside one of the fields, so we have this misdevice registration, which basically tells the misdevice subsystem that this driver is providing a misdevice. And actually, maybe I should tell you what a misdevice is, in case you don't know. So a misdevice is basically the simplest possible driver. So the idea is it doesn't talk to hardware. It's just a file on your machine that you can open, and then you can read and write to it and do other things with it. And those calls basically just go into the kernel. Right? So it's the simplest possible driver that gets you something you can actually interact with. Okay. And so this registration is basically just an object that tells the kernel, hey, there's this type of misdevice that works with this driver. So you can create a file where interacting with it ends up in this driver. And then we have this struct over here, which is basically the instance. So the idea is, every time you open the file, we create one of those Rust misdevices. So we have a second struct here. So there's one per module, and then the second one is, there are going to be many of them. Each time you open the file, you get a new one. I don't know if that's too small. Can you read this? So this is the init function. And I think what's happening here is kind of interesting. On the very first line, what you see is implement module for Rust misdevice module. And so what you're doing here is that, so module is a trait. It's basically a list of functions you can provide for a type. And when you have this implement block, you make this struct usable as a module in contexts that need a module, right? And in the case of module, it's pretty simple. You just need an init function for when the module is loaded. And so this one basically just registers it with a name, and that's it. Okay, some of the thing, yeah. So what I think is more interesting is to talk about this open file. So here we again have the same pattern. You implement misdevice for Rust misdevice. And so this is telling Rust that this struct here should be usable as a misdevice. And then this allows the kernel abstractions to interact with this struct and use it as a misdevice. And one of the required things is the open function. So you need to define what happens when you open it, and you need to provide an instance of this thing when you open. So one kind of interesting thing is, so the C API that all of this talks to has this thing called the private data, which is basically just a pointer. Right? So you get a pointer's worth of space to put your own stuff in. And this pointer thing is where you say, this pointer, I want this kind of pointer to go there. So you're basically telling it, what kind of private data do I have? In our case, the private data is going to be a box of Rust MIST device. And a box is kind of interesting. That's the simplest possible data structure that has allocation. All it does is that it makes an allocation and puts one instance of some type in it. Right, so this is a k-box, so that means it uses kmalloc. So this is a pointer to something allocated with kmalloc that contains one Rust MIST device. That's what we're going to put in the private data. And then we have the open function where we create the box, we allocate some memory, and that's it. Now, this is the return type of open, and you might notice one interesting thing. Result. And so result is Rust's way of handling fallible functions. And so when you see this result of the k-box, then you know that, yeah, this returns a k-box of a Rust MIST device, or it fails. That's what this means. And you may have noticed this question mark, and that's a special operator in Rust called the try operator, which basically says, I'm calling a function that could fail, right? Kbox new allocates memory, so it could fail. Maybe you're out of memory. And the question mark means, if this fails, then stop execution, just return from the function and return the error. That's what it does. So this is sort of an early return. And then here we have the successful return, where we have our kbox, and then we create a result kbox by saying, hey, we are successful. And you may also notice that this is just the last line. There's no return keyword. But in Rust, the last line is returned. What's up?
You wouldn't need the mic. You can just remove the mic.
Correct me if I'm wrong, but you could just have one line there, right?
Yeah, in this case you could.
Without the try operator.
Yeah, you could have written this in a bit shorter way, but I wanted to show.
Okay. I thought I was missing something, but yeah.
Yeah, you can write this shorter, but I think it's more better to show it like this, for an example.
Yeah, sorry, continue.
Thanks. Okay, so as I said, I can't teach you all of Rust, but I at least want to show you how error handling works. And so in Rust, we have this thing called an enum. And if you're familiar with attack union, then that's kind of the same thing. So over here on the C side, you see the equivalent C struct. And so we might say, okay, we have this thing that's either successful or a failure. Let's say we use a Boolean for that. And when it's successful, right, and then we have this union, and so it can contain one of the two, right? It can contain an OK or an error, but not both, because they use the same memory. And so if it's successful, then we have the OK, and if it's an error, then we have the error. And this kind of thing is what this enum thing means in Rust. Rust basically has this kind of pattern built in. And it's what we use for error handling. And so the way it's used is that you might have your fallible function, and you do some stuff, and then maybe you have an error, so you return this error that you can explicitly create like this, and then maybe you return success. And then, of course, if you call it, most of the time, you just want to return the error to the caller if the function fails. So you use the question mark, but there are other options. You could handle the error explicitly, but there's one thing you can't do, right? So let's say you just write fallible, and you just ignore the return value. that's gonna be an error, right? Because you're not handling the error condition, which you should, right? So this is part of how you're gonna find your bugs. Of course, you can explicitly ignore the error if that's what you want to do, but you have to do it explicitly. Okay, so now we've talked a bit about error handling. I want to go back to the example, the MIST device. So we're gonna implement reading and writing. Basically, you write to the file and that the kernel stores a string of what you wrote. And then when you read from the file, you get the string back. That's it. So here's how I'm gonna do that. I have a kvec, so a vector is basically an allocated array, a resizable array that's allocated on the heap. And it's gonna be a byte array, and that's it, right? So we're gonna store our string here. But now the thing you may have noticed is I might call write from 2 threads in parallel, or maybe I'm reading and writing at the same time. So how do you handle that case? And what we're gonna do is do the simplest thing, add a mutex. But this shows another very interesting pattern in Rust, which is that the standard way of using a mutex is that it's a container. Right? So it's not just a log, it's actually a container of data. And so in this example, the mutex contains this other struct, and then in the other struct we have the fields protected by the mutex. This isn't the only way to do it, but most of the time this is how you're gonna protect data by a log in Rust. And if you have a field, here I added another field. If you have another field that is not protected by the log, then you just don't put it inside the container. So it's not in the container, so it's not protected by the log. Can you see this? Okay, so we have writing. So what we need to do here is we need to read the string that's being written, and then we need to store it, right? So the first step is to take the mutex. And so we call log, and this returns a log guard. And those of you who follow what's going on in the kernel, this is actually something we're gaining in C as well. The idea is that inner basically is this object that represents that we own the log right now. And so it has a destructor so that when it goes out of scope, it's going to unlock the mutex. Anyways, so the way that this log guard also works is that, remember, mutex is a container. So anytime you want to access something inside the mutex, you go through the log guard, like this, right? So inner is the log guard, and you have to go through inner to access the fields. And this is how you usually protect data by a log, right? I hope it should be clear that this ensures that you have to take the log, right? Because otherwise there's no way to access the data inside the container. And then, of course, there are the return paths. A function might return in 2 different places. Copying from user space could fail. And then we hit the question mark, and then we just return the error to the caller. And in this case, inner will go out of scope and unlock the mutex. And of course, we also have a return at the end. And so this example shows how with these destructors, you can just return like this. You don't have to worry about your cleanup so much. We also need reading. As you remember, we wrote the thing to this buffer, but now when you read, we need to give the string back. And luckily for us, the kernel has, reading is actually kind of tricky, but luckily for us, the kernel has this function called simple read from buffer that basically implements read from us given a buffer. And so all we're going to do is we're going to call simple read from buffer with our buffer here from the log. Now, one thing we can also see in read is that remember that we had a field that was not inside the container, this device. So it's used for printing, so that you print statements and you know that they're related to this device. Like this print statement comes from the device, that's what it lets you do. And here, notice that we can access that field before we take the log, right? Because it's not protected by the log. Okay, I'm gonna stop with this example now. The example does a few other things. It also has a piece of C code that you can run in user space to talk with the Mist device. So I think you should go check out the example for yourself, try to compile it and try to interact with it. And so if you want to learn more about Rust, then I think the very best place to start is the book. And this is actually, and so the Rust likes to do this thing where they call tutorials for books, even if they're available online. And the book is an example of this. So if you go to the official Rust website, there's the official book, and it's a pretty good introduction to Rust. Of course, it's not kernel specific. I also really, really recommend the Rustlings course, which is basically a bunch of exercises. It drops you down to a file, and then it says, modify the file to do this. And it's a bunch of exercises like that. Another resource I think is pretty nice is Rust by Example, which has a lot of examples of how to do things. So if you like to learn from examples, that's also good. For the case of Linux specifically, I would suggest that you look at the sample code. I already showed you where it is, but also look at the real drivers. Right? For example, the binder driver is upstream. Some of the GPU drivers, or at least stubs of them are upstream by now, and so on. There are other drivers too. So if there's a driver that's similar to what you want to do, go look at it. And also, there's a whole community about this Rust for Linux thing. So if you're going to write a driver, you should talk to us. Ask your questions in our chat room, and yeah. Some other resources that might be useful. Comprehensive Rust is kind of intended for classroom settings, where let's say your company has one person who knows Rust and 5 who don't, then maybe you could have your person who knows Rust teach this course to the others. And then there's this embedded book, which not Linux specific again, but it's kind of similar still. So I think that one might be useful to look at as well. And so, of course, another thing is, what kind of drivers can you write? So we have some kinds of drivers already. And of course, if your driver is not on this list, then you may need to write some more abstractions. But in general, when you're writing a driver for some hardware, you're going to need to support a bus, and then you're going to need to support a class. And the class is the user space interface, and the bus is how you actually talk to the hardware. And we have a lot of the buses by now. Not all of them, but most of them are there, at least on the list. For the user space interface, there are many more of those than there are buses, so it's more likely that you're going to have to write an interface for that. But it's not that hard. You can talk to us as well about that. And some of them are already there, of course. PHY devices for networking, block devices. There are a bunch of abstractions for that. And then MISC, here I'm kind of talking for example, binder. It doesn't have any hardware behind it. It's for talking between processes. DRM, this is where all of the GPU drivers live. Of course, DRM is a very big subsystem, and only parts of it is there, but And there are some other ones going on the list right now. And then, of course, the easy one is, let's say, pure data manipulation. The QR code tool that is in the driver that shows a QR code when your machine crashes, the Rust part is really just pure data manipulation. You get in a kernel log, and it compiles it into the bits on the screen that needs to be shown for a QR code and gives that back to the C code. And then the C code actually puts it on the screen. So that's a really simple use case as well. Of course, your driver is going to need all sorts of other abstractions. You're going to need config.fs or debug.fs or interrupts or mmap or vectors or maple trees, work queues. There's lots of stuff by now. Okay. So I also want to talk a little bit about what can you actually land upstream in Linux if you're going to write something in Rust. Because I mean, in the kernel, we use let's say you take some existing driver and you port it to Rust. I mean, in the kernel, we usually don't really have duplicate drivers. And I mean, I don't think there's a completely hard rule against it. It's kind of up to the maintainers if they want to take that. But I would say the ideal is to pick something that doesn't already exist. One option that people have sometimes done, for example, in the block layer with file systems, is this idea of a reference driver, where you actually do implement an existing driver, but the other driver is kind of intended to be showcase that, yeah, you can actually do all the things in Rust that you could do in C. Another thing we sometimes see is that people just want to implement abstractions for some subsystem without having any driver to use it for. And this doesn't really work because if you want to land your code, I mean, you can send your abstractions, but you really need to have a concrete driver in mind that you're going to use it for, to use it in the kernel. Of course, another possible challenge is maybe your Rust code is the first Rust code in a subsystem. So the thing about Rust is that the goal is for this to become a real part of the kernel, right? Not just some toy. And yes, there's a Rust subsystem that Miguel maintains. He has his own Rust tree. But really, if we have a new subsystem, the ideal is that the existing C subsystem also takes the related Rust code. I mean, this makes a lot of stuff easier. If they change APIs, they have the Rust code in the same branch, so they can change that at the same time. And this is also just the only way this project is ever going to scale. Often when Rust gets introduced, it kind of comes with people too. This is something we see pretty commonly. I have, for example, become some sort of reviewer or co-maintainer, or at least of the Rust parts, and sometimes we even see them starting to help maintain the C side as well. So that might be useful if you're looking for more maintainers for your subsystem. There are also some subsystems that don't want to have Rust, and I think that's okay. We have to remember that there are some pieces of code that everybody is going to need, and so there's going to have to be some flexibility there, but if you're a Leaf subsystem that nobody else talks to, then maybe it's okay. And I also want to talk a bit, so let's say you have this Rust code in your subsystem, but you don't really, it's a new topic for you. Then actually taking this code, reviewing it, and landing it, and seeing what follow-up patches come, this is actually a really good opportunity for maintainers to learn Rust as well. And I would say that one concern that came up in, I think it was Block, is, okay, but we have these really high standards for our C code, and I'm worried that I'm going to land some Rust code that I'm still learning to understand, and maybe there's some bug I would have caught if it was C, and I don't want to land buggy Rust code. But I think the advice that has come out here is that don't let the possibility that the code may have bugs hold you back, right? Say that it's experimental, that it's going to be more buggy than your other code or whatever, at least in the beginning, and then take it as an opportunity to learn, right? And then at some point, maybe you're going to start actually using it in the real world, and then maybe it can become more stable. And by then, you probably have learned Rust a little bit. I would say that, saying that your code is experimental shouldn't be an excuse for like just update the C code, just delete a function Rust is using and break the build, right? I mean, if you do that, then everybody else who's working on Rust in other parts of the kernel, suddenly the build is gonna break. So you're still gonna have to do some stuff to make sure that the code keeps building, right? Otherwise, this is never gonna scale. So that's really all I had to say.
Alice, okay, thank you for the talk. I have a question. So usually, from Rust code, we can call C functions, right? And it's easy. But what about the other way around? Can I have a C function calling Rust code and returning something that I can understand in C?
No problem.
Can I do that already?
Yeah, the QR code generator is an example.
Ah,
So
okay.
if you go look at that, you can see how it's done.
Awesome.
You add the signature to a C header, then you have it in Rust as well, and then if the signatures don't match, it doesn't compile, then you just call the function from the C header like normal.
I'll take a look, definitely. Thank you.
I have an example too. I'll show you.
Okay. Thanks.
Thanks. So I'd love to hear from your experience about iterating on maybe different designs in your Rust code, or maybe if requirements have changed. My perception is that you embed a lot of semantics into the type system with a lot of benefits of doing that. But I also wonder if that could make it difficult to do these kinds of iterations. So just curious about your experience.
It hasn't really been that big of a problem, I think. Like, I won't say that we have never had to change the Rust code because of changes to the C side, but I could probably count it. Like, it's not that many. It doesn't actually happen that often in practice, right? And like, if you're a maintainer and you're worried that this will happen, you know, hopefully your Rust code comes with a person attached to it, and like, and there's also, you know, the rest of the Rust for Linux people who will generally be happy, and they have been happy to help out in such cases.
Okay, thanks.
Could you just take us back to the slide where you implemented write for the MISC device? Great. So is there something in this that says, that tells you this might be executed on multiple CPUs at once?
So this signature is actually a bit hard to see it in, but so in general, the way that it's going to look is that in Rust, you're going to have immutable and mutable references. But these names are actually maybe bad, arguably, because the real difference is shared reference and exclusive reference. And so if you have a shared reference to something, like if your function signature takes a shared reference, then you have to assume that it might be accessed by other threads. And conversely, the mutable reference, then you can assume that it's not going to happen. And so you can basically see it, like there are two kinds of references. And if you look up the definition of this file function, you're going to see it returns a shared reference. And so you know that, hey, this might actually be shared. And the compiler also knows that, right, because it has the type information available.
Okay, so perhaps I phrased that wrongly. What I'm trying to ask is, I'm a big fan of if it compiles, it works, right? So if I didn't know that write-iter could be called on two CPUs at the same time for the same file, I might not realize that the data that's referenced by the file needs to be protected by a mutex. And so I might just, when I'm designing my data structure, I might forget to include the mutex for inner.
Yeah, okay.
Is there anything to protect me from myself there? Okay, great.
So what's going to happen is that you can see here it says &mute inner.buffer. Let's say you got rid of the mutex and you wrote &mute me.buffer. that would not compile because you don't have a mutable reference to me.
Right. Thank you. Perfect.
When do we get field projection so we can have a fancy RC interface into Rust, presented to Rust?
We're working on it.
Thank you.
So you said we should avoid dead code. Say I'm writing a new driver, but the subsystem is not ported yet. So now I have to also port the subsystem and negotiate with maintainers. How is your approach on someone who wants to write a new driver for a subsystem, but the subsystem is not ported yet, and they don't have the bandwidth to port the subsystem as well?
So you're asking in relation to dead code?
No, in Rust, in the kernel in general, say I want to write a driver for, I don't know, the character devices I don't saw listed.
So in that specific case, you should use this device. But okay, let's say you're writing a new interface and the type of device you want doesn't exist. Then you're probably going to have to write it yourself.
So because I cannot ask for the system to be there first before having a use case for it, right?
So you can merge it into the kernel before you merge your driver. But you need to have a driver in mind that you're going to use it for. So in general, it's been okay to merge code before the user, but not without a user, if that makes sense.
Okay.
Hello, thank you for your talk. It was very interesting. I have more of a philosophical question. Right now, would you recommend us to write something in Rust if we want to add a new feature to the kernel, or do you still recommend some C for some specific purposes?
I mean, it's on a case-by-case basis, I think. I mean, if you are writing some code that, for example, let's say you're in some case where you need it to be able to be compiled on GCC, then yeah, people are working on this GCC support, but it's, work in progress. Then that might be a reason to write it in C instead.
Okay, so it's more for a compatibility kind of view.
That's a reason that comes up often when people decide to write something in C. At least when the discussion is started at all. This is a reason I see commonly, right? And people are actually working on two different GCC ways of using GCC with Rust, but work in progress.
Thank you.
So here you have lock, and that looks like guard in the Linux kernel. But in the Linux kernel, we also have scoped guard, which will have a smaller locking region. So in your impression, I mean, I'm sure you can encode one with the other by making extra functions and having smaller scopes. But do you think Rust encourages you to keep locks too long or not?
So there are a few different, so this thing corresponds to, guard, but it's actually a bit more powerful than the direct C equivalent because, for one, you can explicitly drop the lock, like with a line of code. Also, if you just write a scope in your function, like curly brace and then end curly brace, then you can take the lock inside that scope, and then it gets dropped at the end of the scope. Right? So it's not tied to the function, but to the scope.
Okay.
Okay.
So I had this issue a lot with tier as well on Julia. So one of the things I did to sort that out was basically use closures. Because when you use a closure, you create a scope actually. So the idea with closures is you force the scope during which you have the lock, you force it to be as minimal as possible. Because I was facing some issues where I had multiple locks taken and yada yada. It's not necessary, but I think it's a good discipline to, avoid the scenario I've just mentioned.
So in your example, you had a very simple case when you have a mutex which works as a container for a piece of data, but in the kernel code, the locking scheme is often more complicated, and there are multiple ways to access certain things, I don't know, using RCU and mutex and something else. How does this work in Rust, or do you have to fall back to the unsafe code, or it's there is a reasonable way to express it in the type system?
So for one, we have a few different ways of doing it. The most often you're just going to use this container, but sometimes there's a different approach where you have a different container called a locked by, which is then locked by a mutex somewhere else. So that's one way to do it. Of course, if you use atomics, then you don't need a mutex at all, and this also works just fine. If you have some other logging scheme, maybe it already exists, but there's also another interesting option, which is that if you have a new logging scheme, then Rust has this really powerful encapsulation feature that lets you write new logging schemes and add them to the language. So that now you have this piece of unsafe code that you can use safely to provide a new logging scheme if that's what you want. Any other questions?
Hi. So first of all, thanks a lot for this insightful presentation, especially for me, which know very little about Rust. So my question is very simple as well. So you mentioned different types of drivers, different kinds of drivers, and I was wondering how far are we for being able to implement a file system using Rust?
So file systems are a very interesting example. There's actually been a fair amount of work, it's not upstream at the moment, but to write some file systems. And I think if your file system is read-only, I think you can already do it with the downstream abstractions. Okay. And I think there's also work on supporting read-write. So there is some stuff, but I think it would also take some more work to make it fully finished, but you're not starting from zero.
Okay, cool, thanks.
Is that it? Three, two, one. Okay, one more question.
I'm also new as well, so I don't know, for compiling it, right? Say you can't use, the cross-compile architecture. The flags and stuff, right? You can't use GCC. You have to use LLVM, and then have the Rust C available. Correct?
Yeah. So there is some, let's say, experimental ways of using GCC and then the Clang-based Rust C. That there are actually some distros that are doing that, and it seems to work, even if it's, yeah. But in general, I would say the best is that you use Clang and then you use Rust C together with it.
Okay. And then just cross-compiling, just use the LLVM cross-compiling.
Yeah, that works perfectly fine.
Okay, thank you.
Just to add more to it, it's also possible, and it used to be also a default behavior in Rust to use GCC as a linker if your system is, if GCC is the main toolchain of your system. So then in that case, with such setup, you would build your Rust module with the Rust compiler, which uses as a LLVM as a backend, but then it would be still possible to link with GCC.
Okay, thank you for listening.